right, everyone. So today we're looking at a calculus problem. We've got an optimization problem that says find the dimensions that will minimize the cost of making a can. In this case, it's like a cylindrical can, like you can see there. If the top costs 40 cents per centimeter squared, the bottom costs 15 cents per centimeter squared, and the sides cost 50 cents per centimeter squared. The can must contain 200 centimeters cubed. First thing I like to do when I'm working with these problems is one, try to visualize the problem, so I draw something out. And so in this case, it's that can, not much, but there we go. The next thing I like to do is I like to write an equation that describes what I'm looking for. So I'm looking for the cost of making the can, okay? So in this case, the cost of that is gonna be the cost of the top plus the cost of the bottom plus the cost of the sides, or the side, excuse me, okay? So I make up, an expression, not so much, an equation in the sense of, I have variables here and there. Now, for the cost of the top, let's see, and for every one of these, the bottom and the side, let's see if we can make up an equation. Now, the bottom and the top both are circles, right? And this can would have some kind of radius r. So the cost of the top, I would say, would be the area of the top, pi r squared, times 0.40, because of the fact that you have a 40 cents per square centimeter cost, and the total area would be pi r squared. So the cost per centimeter squared times the total number of centimeters squared, that's the area, that's the pi r squared, that gives me the total cost. For the bottom, it's very similar because it's a circle as well, except that it would be 0.15. And the cost of the side's a little, I won't say trickier, but one thing you got to remember about the side of a cylindrical like can like this cylinder, right? Circular cylinder is the more correct way to say it. If you take the side and you unwrap it, you make a rectangle. The width would be like the height, and the length would be the distance around. Well, that's like the circumference, so it's 2 pi r. So total, I'm looking at the cost of the side being 2 pi rh. That would be my total area, because it's the area of that rectangle that you see, times 0.5. Okay, so this right here would be your equation. These are like terms, so let's add them together. And 0.5 times 2 is just 1, so it's pi rh. All right, great. So we have an equation that describes our cost of our cylinder. However, it's in two variables, and we're going to do some calculus here. This is meant for a Calculus 1 class, so we can't really solve it the way it is. So I'm going to have to substitute one of the variables for something else. So that's where what we call the constraint comes in. So you have a constraint which says that the can must contain 200 centimeters cubed. So a constraint basically is, the word kind of implies, is that there is a restriction on the variables. So that 200 would have to be equal to the volume, which is equal to pi r squared h. Okay. And what I can do here is I can solve for either RH, but h is a lot easier to solve for. It would be 200 over pi r squared, as such. So my c would equal 0.55 times pi r squared plus pi r times 200 over pi r squared. Okay. So I replace the h in there, and we're gonna get an equation. And just a note here, with these types of problems, the hardest parts are coming up with, first of all, the equation that models what you're optimizing. And the second thing is the restriction, the equation or the constraint. Okay, and that's typically the two hardest parts. Sometimes it takes a little bit of time to look at what you're trying to maximize or optimize. That's certainly the case when they say, oh, find, for me with this problem, finding the minimum cost, right? I know we have to make the cost as small as possible, but how do I describe it? And the key is to look at some figures about how much, in this case, you're given the cost of per square unit or centimeter squared of your can. So that's how we could determine, oh, it has to be, you have to be working with the areas, okay? All right, and yeah, we now replace the h, and this is an equation in terms of one variable now. And this would be 0.55 pi r squared. Now the pi and the r on the next term cancel out, and you get 200 over r. Okay. And I'm gonna say this, you have a restriction on r from 0 to infinity. Why is that? Because, you can't possibly plug 0 in for your r into that equation. Another way to think of it is r can't be 0 because you'd have no cylinder, because you'd have a radius of 0. And you can make this radius as big as you want. Technically you can have a big, huge radius and a super little height. That would work out here. Technically, that could satisfy the equation of 200 centimeters cubed, okay, for the volume. All right, and then we'll get to that in a minute. Now, the next part is typically like the easiest part for most people, which is taking a derivative. We're optimizing this, so I want to set the derivative equal to 0 or find points where the derivative is undefined, but where first the function is continuous. And if you do that here, you would get this, okay? So I'll let you work on the derivative. If you want to pause the video for a second and verify that, I'd recommend that. So you get 1.1 pi r minus 200 over r squared. And I'm going to set the c prime equal to 0. So you get 1.1 pi r minus 200 over r squared equal to 0. And I'm going to go ahead and multiply both sides by r squared, so I can get rid of that r squared from the denominator. So 1.1 pi r squared times r is r cubed equals 0. So again, multiplied by r squared on both sides and distributed here. That's what I did. Now I'm going to go ahead and isolate the r cubed by moving the 200 over, adding it over, and dividing by 1.1 pi. Okay. So this is what you get. If you prefer, this is like saying r cubed equals 200 over 11 tenths pi, which is 2,000 over 11 pi. So we take the cube root of that. This equals the cube root of 2,011 pi. And you can certainly leave your answer like that. If you want to simplify this a bit more, you can say the cube root of 2,000 times the cube root of 11 pi. 2,000 is like saying 1,000 times 2, and the cube root of 1,000 is 10, so you can pull that out. And we get this value of all r, but how do I interpret this? What does this mean at the end of the day? Well, what this can mean that it could be the minimum for this function in terms of if you let r equal this value to minimize the function's values, so min y value per se. So certainly have that. And 99% of the time with these types of problems, the value that you get, if you only get one value, it's going to work out. However, you need to prove that. There's a couple ways of proving it. One way is to, sorry, I'm going to write this out again. Pi r minus 200 over r squared. I can go ahead and take a second derivative and use what we call the second derivative test. And the second derivative test says that if you take a second derivative and you plug in a critical point, and based on the sign of the second derivative, it tells you something. Okay, so I'm not going to give you all the results of that test here, but I'll just say that it's something that you got to look up, just the results that each of the signs of the second derivatives gives you, okay? So in this case, our second derivative is positive. Yeah, I don't care about the actual number, I care about the sign, excuse me, that was a cube. And this whole thing is positive, so because the second derivative is positive, by the results of the second derivative test, it says that r equals 10 cube root of 2 over cube root of 11 over pi gives a absolute minimum, okay, for our case, because there's only one minimum value, that's why, okay? So yeah, there's no more critical points, and it came out to be a minimum, therefore it's got to be an absolute minimum. And therefore for our dimensions, my r would be this, and then my height would be, well, I go back to my equation that relates height and radius, which was this right here, sorry, 200 pi over r squared. And yeah, your height would be 200 pi over 10 times the cube root of 2, cube root of 11 pi, all squared, okay? And whatever those numbers out, if you crunch them out with a calculator, you know, if you need to see that, and that means by all means, go ahead and do that. But that's what the dimensions would be. Now the second way to figure out whether you'd have a min or a max here, I went over the second derivative test. The other way would be to do a number line. You would have 10 cube root of 2, cube root of 11 pi. Here would be 0 because that's as far as our function for r can go, and then from there. And you would pick a couple numbers, and what you would get is you would get a minus and a plus here, which tells you technically you'd have a relative minimum, but because this is the only relative minimum, and a couple other things, if you want to be more rigorous about this, this would be an absolute minimum, okay? And let me go back to the top of the problem here. And that was it. You were asked for finding the dimensions, and there you go. You're not actually asked for the volume here. And that would be it. So your dimensions would be r to be that, and then your height to be that in terms of centimeters. Okay, sorry, don't forget the units as well. Okay, all right, I thank you for your time. Hope this helps.